Thank you so much for checking in on Henry AI Labs. I'm currently taking some time to focus on my PhD research, so instead of the AI Weekly Update series, I'm going to switch to a one paper summary video a week series. So I'm still going to try to curate the content for the Weekly Update series and link it as a Notion page in the description of these videos, as well as starting a new GitHub repository for AI Weekly Updates that will contain just the every week's Notion page for the AI Weekly Update content. So with respect to my PhD research, if you're interested in helping me out with survey papers on text-to-image generation or data augmentation controllers like auto-augment, fast auto-augment, population-based augmentation, these kinds of ideas, please see the write-up in the description or stay tuned to the end of the video for more details on that. This video will explain challenges in generalization in open domain question answering. I picked this paper to summarize this week because I'm really curious in these papers that are breaking down these different categories of generalization. Say the difference between compositional generalization compared to the general setting of in distribution versus out of distribution, or maybe domain generalization with things like, say, domain net, where you transfer from photograph images to sketches to cartoons. This kind of domain transfer compared to these ideas like compositional generalization, where you need to combine these different parts of previously encountered training data and then combine them into new configurations in the test set, and that's the specific kind of generalization. So I'm really curious in this idea of breaking apart the specific kinds of generalization that occur, and then this idea of open domain question answering, a pretty ambitious problem where you're trying to, say, answer any kind of question. The difference between these, as they call them, non-parametric models, where you have the retriever component as well as the reader component. So you have something like dense passage retrieval that retrieves relevant documents for answering the query and then attends over the retrieved documents to generate the answer, compared to, say, papers like how much knowledge can you pack into a language model, where you try to just have one language model that can just generate the answer to any question. But a very interesting setting, open domain question answering, taking apart the different test questions that appear in these data sets and then categorizing the kinds of generalization that they require. Generalization is the big goal of deep learning, trying to achieve models that you can train them on a training set, and then when you evaluate them on new test sets, new data that hasn't been seen before, it performs well and is able to classify them, or say if it's generating images or generating text, it can write new images. It hasn't just memorized the images that it's seen in the training set, and so on, and it can generalize these new ideas. So the standard approach for evaluating generalization is where you take your entire data set and then you just split it into random trained test splits. And this is this idea of independent and identically distributed. You say that the training and test splits come from the same distribution of data, and that the way that you sample the test set has nothing to do with how you sample the training set. It's random. They're not dependent on each other. So there's been some recent research on studying how this test set will differ from the training set and how that will impact this generalization metric. So say you have things like corruption tests, where the test set is different from the train set because you've added noise to it, you've done data augmentations to it, or whatever it is that you've done to have this corruption test. Maybe it's an adversarial test, and that's the difference between the test distribution and the train distribution. This general idea of out of distribution generalization. Say you train it on MNIST digits, and now you're evaluating it on the Street View house numbers data set. This idea of this as being an out of distribution kind of image. Domain generalization, probably the domain net paper and data set is my favorite example of this, where you have the same categories of images. So you're holding that constant, where you have like airplane, basketball, basket, these kind of ideas, class labels. And then the domains are the like artistic style. So if it's a photograph, a sketch, a cartoon, a painting, so you're transferring from these domains. And that's one idea of thinking about domain generalization. Also in natural language processing, maybe things like news articles to biomedical papers or computer science papers, these kinds of ideas of hopping from domain to domain, from papers to IMDb movie reviews, these kinds of ideas. And then really this data set called WILD is really exciting with real world distribution shifts. So this has things like wildlife monitoring cameras, hospitals that shift, and really trying to capture this idea of distribution shift and particular differences between the test and training set in real world applications. And then studied in this paper is compositional and systematic generalization. And this is maybe the most interesting kind of categorization of generalization that's been being developed. And this is the idea of particularly taking apart parts of the training data and then reconfiguring them into novel compositions for the test set. So this idea of, say, the avocado armchair from Dolly, you've been able to decompose this concept of avocado that's in the training data and then the armchair, and then the style and you're recombining them to these new compositions, and that's the difference between the test set and the training set. With that quick overview, the authors are identifying 3 kinds of generalization that is required for these open domain question answering datasets like natural questions, web questions, or trivia question answering. So the first of which is overlap, and this is where there's a significant overlap between the test question and one of the questions that appeared in the training set. So who won the first Nobel Prize in physics? Who got the first Nobel Prize in physics? This is a difference in the form of the question. So it's not a novel entity, as we'll see later. It's seen this idea of Nobel Prize in physics, and it's not some completely novel composition of the question, who won, who got, similar kind of structure in the question. As a huge topic of this paper is this idea of question decomposition, trying to use things like semantic role labeling in order to decompose the different forms of the questions that appear, and that's a major topic of this idea, is trying to see the different structures of questions. So just as a high-level overview of who won the first Nobel Prize, you might say who, the WH is the question word, and then this is like a supporting thing, and then this is the entity. You replace it with entity, in, entity, as one kind of style of these questions. So when did the first entity come to entity, this kind of idea. So this is overlap, significant overlap in the test question, has appeared in the training set really. And then compositional generalization. So here's the idea of compositional generalization. In the training set, you have these 2 kinds of questions. Cow is a national animal of which country? When did the first panda come to America? So the new composition is to take this panda entity and then use the same structure, the question style of is a entity, and then append this second part of the training question. And then novel entity generalization, interesting thing with question answering where you're asking it to answer a question about something that it's never seen in the training set. So naturally the parametric models, like trying to use BART large, T5, with only the pre-trained training set rather than having a retriever component that's going to say retrieve something about the song The Glory of Love, so you actually do have some information to read and then answer this novel entity test. But this idea of it's trying to answer some question about something it's never seen in the data set before. A key player in making this idea work of decomposing these questions and then determining if it's a novel composition or if it has significant overlap and how the entity plays in with this also novel composition of the question, and also relating to this massive theme in deep learning research, which is this paper climbing towards NLU on the difference between meaning versus form. Title is similar to that. I'm not sure if that's exactly correct, but this idea of having this automated semantic role labeling system to do the question decomposition and to assign these categories of questions and then say this question type frequency and say things like how the frequency of this question type is impacting the generalization between the distribution of how often you see a question like who is the entity in entities, or say when did the entity do entities, things like this, maybe like this kind of structure of the question. So here's one example of it, and then we'll go to the paper in Appendix A. They have more examples of these question decompositions. I'll just kind of give some evidence of what this looks like, this idea of having these semantic role labeling pre-trained models to parse each question. So here are some more examples of these question decompositions where we use pre-trained models in order to classify whether it's the question word, the verb, or other arguments, and then Wikipedia entities. So these entities are, I think there's probably some set of Wikipedia entities that they are linked to. So this task of entity linking, another one of these kind of natural language processing semantic role labeling tasks. So here are some examples to get a sense of what's happening with this. Who is the owner of Reading Football Club, or Reading Football Club, labeling the question word, the verb, the other arguments, and then the entity. So this would be one question style, to have the question word, verb, other arguments, the entity. So just thinking about the ways that these questions appear, so it's kind of this idea of linguistic form, linguistic style, and how this is biasing the performance of the model because of the way that the questions are presented rather than the actual ability to retrieve information and answer questions, compared to say it's overfitted to one kind of question style. So hopefully that's more clear from looking at this. I also think it's kind of confusing to think about how to break apart these questions and decompose them into different categories based on the structure of the question word, the verbs, and this kind of idea. So to define it with this idea of using the question decomposition model, these are how they're defining the different generalization sets. So we have the overlap questions where you have a lot of similarity. If the question, the entity appears in the train set, and then this new question that you're testing, then it's also going to be in the test set. So say you're talking about the Empire State Building, you have a question about this in the training set and the test set. This is the idea of overlap. And the Q prime in this case, I think, being the the named entity that's being classified. So compositional generalization is saying that it has all these parts are in the training set. So these Q1 prime, Q2 prime, these are the decomposed different components that make up the question, and this characterization, all these individual components appear in the train set, but this particular question doesn't have the exact same decomposed question structure as the new question. So hopefully that makes some sense. And novel entity, this named entity, so I guess S is for the named entity, something like that, it has never appeared in the test set. The authors are going to classify the occurrences of these three types of questions in these three data sets. So we have natural questions, web QA, and trivia QA, different kinds of question data, information seeking. This is a really great paper on a survey of recent question answering data sets describing how they're different from each other, how natural questions is different from trivia question answering, and all these interesting ideas in question answering research. And then also, if you want to test any of these data sets for yourself, I highly recommend checking out the Hugging Face Datasets library. They have a Streamlit interface for quickly seeing examples of these datasets, as well as data loaders for using it in, say, PyTorch, Keras, or TensorFlow. So they're going to be classifying the test questions from each of these three sets into overlap, compositional generalization, and novel entity for, again, natural questions, web QA, and trivia QA. So here are some examples of how these test questions are being categorized into these three generalization categories, and pretty similar to the image at the beginning of the presentation, but here's just another look at this. So we might say we have this question appears in the training set that's used to fine-tune the models or train it entirely from scratch. So say you have something like who won the first Nobel Prize in physics, and then the test question is who got the first Nobel Prize in physics. So these two entities, and you say generally the question structure. I'm not sure exactly how you say the difference between got and won and these question decomposition ideas. Maybe it's question, word, verb, entity, and entity, that kind of question structure. And again, I think this is an interesting idea to completely take apart how you're decomposing these question structures and then accounting for that. And I think that's one of the huge takeaways from this paper is understanding the frequency of question styles that appear in these trained test data sets for question answering domains. So then here's an example of something that's not overlap. And I think the difference here is because it says the Super Bowl. So when did the Philadelphia Eagles last win the Super Bowl compared to when's the last time the Patriots played the Eagles? So you have this as more of a novel entity. So if Patriots never appears in the training set, but just for this particular question, Eagles, Super Bowl, it's not the exact same entities that appear. And then also you might say the composition is different. So when's the last time the entity, verb, the entity, or last verb, I guess, but it maybe is a simple composition. And I think this compositional part in the question decomposition for me personally is a little bit ambiguous, but here's an example of the compositional generalization. So when is the next fairy tale, or when is next fairy tale episode coming out compared to when is the next scandal episode coming out? So these have the same compositional structure, even though you're replacing the entities. And that's the idea of compositional generalization. You've learned this composition of the question entities, but you're switching it in with new parts of the training data with new entities, replacing the scandal fairy tale with scandal. And then novel entity, this new song that is never seen before in the training set. The authors are comparing the generalization differences between non-parametric and parametric models. The difference between having a retrieval component that's going to append to the input some retrieved documents, like say you have this novel entity like who wrote the song The Glory of Love. The retriever model is going to retrieve paragraphs or whatever it can from Wikipedia that will help answer this question. So it dramatically facilitates the novel entity kind of generalization to retrieve some kind of information. So particularly here, the different kinds of models that they're testing, they have the retrieval augmented generation model, which is the combination of dense passage retrieval, where you say learn vector embeddings for all the documents in the document index, and then you have, say, maximum inner product search, some way of doing a nearest neighbor search for returning the query, the nearest neighbors from the query encoding with the encoded documents. And then you use the BART encoder-decoder model to attend over these documents and generate some kind of answer. And then you have the fusion in decoder architecture, the difference being that each document returned from the dense passage retrieval nearest neighbor thing with the query is independently encoded by the T5 large encoder, and then the decoder attends over this encoding to generate the answer, as well as the document representation. So this is a bit different of exactly how the key difference is just how you're processing the retrieved documents and how you're having this flow of information through, say, separate Siamese encoders, or just right into encoding all the documents, generating them in the BART architecture. These two different styles of doing that. And then you have the extractive model. This is where you retrieve the documents and then you classify an answer span. So sort of like the squad data set, you classify the answer rather than generating the answer. And then this is supposed to be repack. This is a data set where this is a model where the document index for the retrieval model is made of question-answer pairs. So they have this question generation approach. This is another paper from I think most of these authors, that they have this way of generating questions from the Wikipedia corpus, or whatever the corpus is, so that the document index is question-answer pairs, not just information to be returned. So you're returning question-answering pairs from the retrieval step rather than just raw information. And in the parametric models, this has no retriever component. You're purely just trying to answer the question with the language model. And this is testing the BART large model and the T5 11 billion parameter model. Here are the results comparing the non-parametric models with the parametric models on natural questions, trivia QA, and web questions, breaking down each category of test question based on whether it has significant overlap with the training question, whether it's an example of compositional generalization, or if it's a novel entity appearing in the test set that wasn't in the training set. So you can pause the video if you want to look at these. The next slide will go through the high-level overview that the authors present. Probably something quickly to look at that I think is really interesting is the performance difference between RAG and FID. RAG just having this BART encoder-decoder compared to the separate Siamese-style T5 encoder decoder thing. I'm surprised that that's so much better in these results. I think that it's like a subtle difference. Maybe it's a large model, also these kind of details, but this kind of difference is interesting. And then also the repack, this idea of storing question answering pairs rather than documents, also seems to perform well. This is a pretty interesting idea because it's kind of like this idea of task alignment, domain alignment, things like the lessons of Don't Stop pre-training, where they say that basically the alignment between this pre-training system you're building with the downstream task is important for performance. And you see that little gain with storing question answer pairs rather than just raw information. And then the extractive model that is classifying the answer in the retrieved documents also isn't too far off of the other models as well. So, and then also the non-parametric heavily outperforming the parametric models, except for, interestingly, overlap. So when the test question has appeared basically in the training set, the parametric models perform better than the non-parametric retriever models at this kind of test question. Here are some takeaways the authors note from the exact match results on these different categories of questions. So the first of which is the overlap questions can be memorized. The parametric models that just store all the knowledge in their parameters can answer these significant overlap with the training set in the test questions. The next of which is the non-parametric models are better at novel entity questions. This makes a lot of sense. How could the parametric model answer a question about an entity it's never seen in the training set? And then the non-parametric models perform worse at the compositional generalization questions. So the parametric models have maybe learned more about the form. In this table, I think it's the web questions one more so, that's showing this difference where you have the compositional generalization being performed better by the T5 11 billion with the salient span masking pre-training strategy. And then you have the more analysis of the performance of the parametric models on novel entity and compositional generalization questions if you want to check out the paper. And then probably most interestingly of this result is that the retriever gains aren't really maxed out. So this is the top 20, top 100, as you have this retriever component and whether the gold answer, the ground truth answer, is contained in the top 20 retrieved documents. So as you start going to compositional generalization and novel entity, the retriever stops actually being able to generate the answer in the retriever component. So the reader can't generate it if it's not even in the retrieved documents for these non-parametric models. So here's an opportunity to improve these models in the retriever side of it. So from these results, the authors are going to break down the performance of the non-parametric models, starting with probably the most interesting theme of this paper, this idea of compositional generalization, and then question pattern frequency, having this question decomposition, categorizing these types of questions and how often they appear. So how often does the type of question, who was the entity of entity, say that appears 1,250 times in the training set compared to how many entity are an entity? This kind of question only appears 32 questions. And then you have this kind of class imbalance setting with the style of the question, and this is biasing the performance. So trying to study this, how the frequency of these different question patterns, categorizing the question patterns, and using that to gain more insight into the generalization for question answering systems, and then in this case particularly open domain question answering, where you have to answer a question about anything. One of the most interesting topics in natural language processing research is this difference between meaning versus form. So in this paper, Climbing Towards NLU on Meaning, Form, and Understanding in the Age of Data, the authors argue that these natural language processing models that are achieving say state-of-the-arts on the GLUE benchmark, SQUAD, these kinds of natural language processing benchmarks, they don't really have the meaning of language. They've just overfitted to the form. So an example of that would be if all the test questions have the same form that appears so often in the training set, it's overfitting to this form of the question. It won't generalize to more flexible forms of the question. It won't adapt to novel entities, compositional generalization, these kinds of ideas that they're trying to break down these types of test questions in this paper. So here's an explanation of the octopus example in meaning versus form that kind of illustrates this idea of meaning versus form. So you have two people separated on stranded islands and they communicate with an underwater cable. So the octopus intercepts the underwater cable and eventually it has so much form of language that it can put itself into either spot of the islander and talk to the other islander and go undetected. But when there's a novel entity like a bear appears on the island and this stranded islander goes, help, a bear, the octopus has no idea what a bear is. It's never seen it in the training set. So it doesn't really have the meaning. It just has the form of their communication. And that's the illustrative example to describe this idea of the style, the form of language compared to the actual meaning of it, and then trying to understand how the form is influencing the generalization in this paper on open domain question answering. This plot is showing a positive correlation between how often the question type appears in the training set compared to how it's performing on the test set. So what this is showing is when the question type, the question pattern only appears 0 to 1 times, you have an exact match score of say 0.4 or I guess 0.9 when it's an overlap. So you're seeing the exact same kind of thing in the test set. And then as you are seeing the test question has appeared 1 to 25 times, 25 to 50 times, or greater than 5,000 times in the training question. And then I think this plot is a little confusing for me, but it's a distribution of how often the test questions are in each of these buckets. So how often the test question has appeared greater than 5,000 times, the pattern of the test question has appeared in the training set, and then also for these categorizations of overlap, compositional generalization, and novel entity. Whereas the appearance of the question patterns being more frequent was positively correlated with performance, if the entity appears often, it's negatively correlated. So if you say have a ton of questions about the New England Patriots or whatever it is, that is actually negatively correlated. But they describe why that is, and it's because of the time-sensitive nature of a lot of these things. So this paper, Time-Aware Language Models as Temporal Knowledge Bases, this presents this idea that you need to have some kind of signal of what time, because these things change. The junior senator from California, you have a new election, and now there's a new senator, so on. So you need to have this kind of time signal for these questions, and that kind of explains why the more often the entity appears, the more likely the retriever is to grab something that's old and outdated and not the gold answer. The authors further explored this idea of the difference between the compositional generalization test set and the novel entity test set. So the results are confounded by a lot of these novel entity test questions could also be categorized as a novel composition of the question style. So when they hold the pattern constant, fix it constantly, and then replace the novel entities with seen entities, the results are mostly unchanged, so showing that it's not the unseen entities that are the bottleneck for these models, it's the novel compositions, the novel question styles, which is a really interesting takeaway of the study. So some of the key takeaways of the study of understanding the performance of the non-parametric, the retriever models, the retriever read models is kind of like RAG, FID, this idea, is that you have cascading errors from the retrieval component. It's not really retrieving the gold answer in the top 20, top 100 thing as we saw earlier. The frequency of the question pattern helps, and the frequency of the entity hurts, and as explained by this time-sensitive information thing where the answer is changing over time, so it has outdated information that it's retrieving and then fetching the answer in the outdated information. So this paper presents an interesting idea that the compositional generalization is a huge hurdle for solving this open domain question answering problem. And here's another interesting paper about hurdles to progress in long-form open domain question answering, and also illustrated in the Google AI research blog. So here's some of their takeaways that they had from studying this problem of, in this case, it's long-form open domain question answering. So it's not just answering some new entity with like some new question with a quick answer. It's generating these long answers to questions like this. And you can imagine there's novel compositions of these questions, novel entities that appear, the same kind of problems that have been studied in the paper we just looked at. So they also conclude with this idea that there's a lot of train test overlap. This idea of overlap is a frequently thing, as they categorize about 33% of the questions in natural questions, web questions, and trivia QA have this overlap problem. They find problems with the automated metric, say this Rouge score or exact match, this kind of problem for how you evaluate question answering systems. And then they find also this lack of grounding. Maybe we could think of this as novel entity generalization, or this idea of Grounding is like this idea of meaning, understanding, the help a bear example in the octopus thing. Grounding where you have some kind of basing of the language in some, maybe it's multimodal data, or maybe it's like these ideas of, say, AI story generation where there's some grounding that is text as well. But anyways, this idea of experience grounds language and so on, and maybe the novel entities is the best comparison with this paper for this video. Taking a step back from open domain question answering and just looking at this problem of compositional generalization more broadly, we've seen a lot of different uses of this word and interesting kind of ways of defining this idea of compositional generalization. So here's a really interesting picture where you have this novel composition of, say, the moped, the motorcycle, and the unicycle to form these new kind of objects. And this is kind of like the avocado armchair example. This is one way of thinking about what it means to have compositional generalization. This is another data set, the Clever data set, where you have the composition of these different objects, and then you're answering questions, a visual question answering data set where you say, are there an equal number of large things in metal spheres? And you have to parse a scene, and you can have novel compositions of the scenes, and it can be procedurally generated and these kinds of ideas. And then this idea, is this an example of compositional generalization where you have, say, fact chaining, multi-hop question answering, where in this case, if you say Bob is green, you need to go to, if someone is, all rough people are green, and you need to see, is Bob rough? No, Dave is rough. So this idea of fact chaining, is this an example of compositional generalization? And then another interesting thing is this pointer value retrieval data set, where you have to, say, reason around the data set. Is reasoning, is this kind of reasoning skills? This is the same idea as compositional generalization, but in this case you have to look at the top left, and that tells you where to find the answer, and then you have new compositions of how to search for the answer in the image and search for what to do and so on. So this other categorization of novel entity generalization seems really similar to me of zero-shot learning, which is easily one of the most active areas of deep learning research, things like prompting and the GPT-3 in context learning, and now this recent paper from researchers at Google that is also exploring a 137 billion parameter model and how well it can do zero-shot learning. So in this latest plot, showing this gain of zero shot compared to GPT-3's few shot. So in zero shot, it has not even seen, there's no prepended context, there's no prompting, it's just given the new inference and it can just do it. So that's kind of like novel entity generalization, I guess, taking apart the different kinds of zero shot learning and this kind of idea. And then maybe also envision this kind of few shot learning, this quick adaptation. This is kind of an idea of that, where you have these examples in the few shot context and you're learning the novel entities like this new name, and you're saying this is a DAX now, this is a Blicket now. This kind of idea of having this novel entity, maybe you'd have some new object entirely, and these kind of ideas, maybe you're thinking about how to adapt this to image classification, these kind of well-studied problems. So one of the most important things to look at when studying generalization and distribution shifts is this recent data set that's come out titled Wilds, a benchmark of in the wild distribution shifts. This is a collection of real-world examples of how the test distribution changes from the training distribution, and as we see examples like compositional generalization, novel entity, trying to really break down these different categories of generalization. So the way they define the two distribution shifts in Wilds are either domain generalization or subpopulation shift. Subpopulation shift being, say you have these class imbalance data sets where you have a minority instance that appears more frequently in the test set than the train set, and then domain generalization where there's no overlap between these domains. So in Wilds, each data set is a XYD instance where the D is the domain that it was sampled from, or the distribution that it was sampled from, if you want to think about it like that. So domains, things like domain net, where you have the sketches, the photographs, the paintings, these ideas of shifting the different domains with the generalization abilities. And here are some examples. The wildlife monitoring, where you have the same location, so you see the background's the same, it's the same wildlife monitoring camera. So this is the in distribution example, and then out of distribution is generalizing to a new wildlife camera, and then more examples of, say, the lighting effects of images in different hospitals. So with respect to being able to categorize these different kinds of generalization, I think it's interesting to think about how we can use data augmentation as a solution to these problems. So if we're able to decompose the different kinds of questions that appear in the training set, test set difference, we could just artificially create questions of that form and then balance out the question distribution through data augmentation. And there's some interesting cases of using this kind of generation to endow these models with these skills. So in turning tables, they show that these test questions fail at symbolic queries. So say aggregation queries, list queries, these kind of things. So what they do is they use this table to text approach to generate training data that fits this template of the generalization task for the difference between, say, a language model in Wikipedia to answering symbolic queries, and you can just kind of generate this data. So if you know what kind of generalization is going to be required, you can probably shape the data in that kind of way in this kind of data augmentation solution. So this is kind of the idea behind generative data augmentation. Can generative models like GANs or the vector quantized variational autoencoder, can they simulate these kinds of generalization distribution shift tests and then distill it into the discriminator? So say you want to have this novel compositional generalization thing, maybe you can create that training data using like Big GAN or Dolly or something like that, and then put that into the classification model. So I think it's also interesting to think about the differences in generalization between generative and discriminative models and how that's measured. This paper on the steerability of GANs, looking into the latent space of GANs to kind of explore the generalization, see if they can find data augmentations like zooming in, rotations, these kinds of ideas. And then the classification accuracy score, which is where you evaluate a generative model based on how well that data would be for training a classifier evaluated on real test sets. And then I think this Dolly avocado armchair is just an amazing example of achieving this kind of compositional generalization as it's described in these papers, particularly in this one where you're combining the moped thing. This seems to be kind of solved with the Dolly model. Thank you so much for watching this overview of challenges in generalization and open domain question answering, a really interesting study breaking apart these different kinds of generalization that's required in the test questions for open domain question answering datasets like natural questions, web questions, or trivia QA. We have the overlap, this really exciting idea of compositional generalization, and then novel entity generalization. They see better performance with novel entity generalization with the non-parametric retrieve then read models, whereas the parametric models are better at the overlap and the compositional generalization questions. It's an interesting opportunity for exploring these behaviors more, and the difference between these retriever-reader versus solely storing all the knowledge in the parameters of a language model. So as mentioned quickly in the beginning of the video, I'm looking to recruit collaborators for survey papers on text-to-image generation and data augmentation controllers. Text-to-image generation, I'm really curious about, say, not only just the Dolly model and the vector quantized GAN and these kind of approaches of having this vector quantized dictionary and then using the autoregressive model to just model these discrete latent codes and these kinds of ideas, but also say image editing applications, how the image-to-image translation like CycleGAN has been influenced by adding the text control signal as well, and then how these can be used for things like generative data augmentation, the idea of using the compositional generalization achieved in Dolly to test it, distill it into discriminative models in the kind of classification accuracy score style of evaluating. I'm also really curious about these data augmentation controllers, studying things like auto-augment, fast auto-augment, population-based augmentation, basically the intersection between AutoML, hyperparameter search, and data augmentation, but also things like, say, generative teaching networks and synthetic petri dish, these kind of out-of-the-box ideas of thinking about how to say it's kind of like a teacher-student gradient thing where you have the outer inner loop and then you put it all the way into generating the augmentations or generating the data itself. So these kinds of ideas of thinking about how to have this meta level of controlling data augmentation. So if you're interested in working together on any of these survey papers, please send a quick summary of your thoughts about these ideas to cshorten2015@fau.edu. Thank you so much for watching this video. Please subscribe to Henry AI Labs for more deep learning and AI videos.